This is Beyond the Business.
We often talk about change as something ahead of us, something we still have time to prepare for. But when it comes to the ocean, the shift is no longer a projection. It is the environment we already live in. The world we operate in today is shaped by processes that have been unfolding for decades, not as sudden disruptions, but as the cumulative result of human activity, both intentional and unintended. What we are witnessing is not an anomaly and not a temporary deviation. It is the emergence of a new ocean, a system that continues to evolve, respond, and influence the conditions under which societies function. This is why the conversation cannot be limited to adaptation as one time response to a new normal, because there is no fixed normal to adapt to. Instead, the challenge is to understand how to operate within a moving environment to align planning, infrastructure, and decision making with a medium that is changing in real time. The question then is not how we adapt to the ocean, but how we learn to think, build, and act within a world where the ocean itself is in transition. If the ocean we live with today is no longer the one our systems were built around, then the question becomes how we actually see and interpret this change. This is the ocean of waste. For decades, our understanding of climate and marine conditions has been shaped by maps. Temperature maps, circulation models, seasonal patterns, long term averages that helped us translate complexity into something predictable. These maps were never just visual tools, they became the reference points for navigation, planning, infrastructure, and even for how societies understood risk and stability. But maps are built on assumptions of continuity. They describe patterns that are expected to hold, ranges that define what is considered normal. What we observe in today increasingly challenges those baselines. Measurements from monitoring systems, satellite observations, and oceanographic services show shifts that move beyond historical ranges, not as isolated anomalies, but as an emergent patterns. This does not mean the maps were wrong, it means they were created for a system that behaved differently. And when the behavior of the system changes, the tools we use to interpret it begin to lag behind the reality they are meant to describe. So the challenge is not simply to update a set of charts, but to recognize that our framework for understanding climate was designed for a more stable ocean than the one we have now. When we look at the data coming from Copernicus Marine Service, what becomes clear is not just that the ocean is changing, but why these changes are happening. Take sea level rise, for example. It is often associated only with melting ice, but a significant part of the increase comes from a more fundamental process. As the ocean absorbs excess heat trapped in the Earth climate system, water molecules move more energetically and take up more space. The result is subtle, but cumulative. The ocean expands and global sea level rises year after year. The same heat uptake explains the record sea surface temperatures observed in recent years. The ocean acts as a vast reservoir, absorbing the majority of the excess energy generated by greenhouse gas concentrations in the atmosphere. This stored heat does not remain static. It alters stratification, weakens vertical mixture, and reshapes temperature patterns across basins. Changes in salinity reveal another layer of the story. Warmer air intensifies evaporation in already dry regions, while increased precipitation freshens others. Over time, this amplifies the contrast. Salty areas become saltier and fresher regions more diluted, signaling an acceleration of the global water cycle. Ocean currents in turn respond to these shifts in heat and density, As temperature and salinity gradients evolve, the forces that drive circulation adjust, subtly modifying the pathways through which heat and nutrients travel across the planet. What Copernicus' observations ultimately show is not a collection of isolated indicators, but a connected system reacting to an energy imbalance. Sea level, temperature, salinity, circulation, each change is a different expression of the same underlying process. The ocean redistributing the excess heat of the planet. If we step away from charts and measurements for a moment and look at what these changes mean in real places, the picture becomes much more tangible. In the Pacific, on low-lying islands nations like Kiribati and Tuvalu, the ocean is not rising as a distant projection. It is moving into everyday life. Coastlines shift, storm surges reach farther inland, and fresh water sources slowly become brackish. The land itself remains, but the conditions that make it livable are quietly changing. Far to the west, in the Mekong Delta, the ocean shows its influence differently. During dry seasons, salt water travels upstream, seeping into soils that once supported rice fields and orchards. Farmers adjust what they grow, not because of a sudden event, but because the chemistry of the water beneath their feet is no longer what it used to be. In Australia, the Great Barrier Reef tells another part of the story. When ocean temperatures rise even slightly beyond their usual range, corals experience stress, losing the color that signals as a healthy ecosystem. Some recover, others don't, but each heat event leaves a visible mark on one of the most complex marine environments on the Earth. And then there is the North Atlantic, where change is less visible but no less powerful. As glaciers in Greenland lose mass, the fresh water enters the ocean, reducing salinity in key regions and subtly altering density patterns. Because ocean circulation depends on these gradients, even gradual shifts can influence how heat moves through the basin. A warmer ocean surface stores more energy, and when that energy interacts with atmospheric system, it can contribute to stronger winds, more intense storms, and a climate that feels increasingly unsettled along Atlantic coasts. Taken together, these places are not isolated cases. They are different expressions of the same process. An ocean adjusting to a new energy balance. And when the ocean adjusts, its influence travels through coastlines, through agriculture, through ecosystems, and through the weather patterns we experience every year. In the Atlantic basin, the shift is not theoretical, it is visible in the timeline of recent years. In 2023, powerful storm systems across the North Atlantic forced vessels to delay departures and wait for safer windows. A reminder of how quickly the English Channel and nearby routes can become operational bottlenecks during severe weather. By 2024, events like Hurricane Debbie again showed how quickly maritime schedules can unravel. As storms approach, ports suspend operations, traffic slows, and once conditions improve, the recovery itself takes days or weeks. In 2025, extreme winter systems sweeping across northern Europe triggered storm alerts across major ports, from Rotterdam and Hamburg to the English Channel. High winds and rough seas led to berth closures and restricted vessel movements across the region. And in early 2026, the pattern repeated with even greater clarity. Severe Atlantic weather stretching from Morocco to the entrance of the Channel forced shipping lines to hold vessels in safe positions while navigation conditions deteriorated across the Bay of Biscay. Across these events, the operational effect is immediate. Ships wait at sea, schedules slip, cargo pauses mid journeys. But waiting does not mean inactivity. Engines continue running, power systems remain online, and fuel is consumed simply to maintain safety and readiness. So every prolonged storm window carries a hidden energy cost. Emission released, while the supply chain itself stands still. Over the time, these interruptions form a pattern. Weather volatility does not just delay movement, it reshapes efficiency. The ocean becomes not only the root of global trade, but a factor that directly influences how reliably and how efficiently that trade can happen. In the Pacific, the scale of El Nino is visible in hard numbers. Of Peru, the world's largest anchovy fishery has repeatedly seen catches drop by more than half during strong El Nino events. In peak years, landing above 5 million tons have fallen to around 2 million as warm surface waters suppress nutrient upwelling. The 2015-2016 El Nino brought intense rainfall to northern Peru and Ecuador, flooding damaged transport corridors and port access, while tens of thousands of hectares of farmland were flooded, leaving agricultural output reduced to multiple seasons. During severe El Nino related flooding along the Peruvian coast, operations at several regional ports were periodically suspended as sediment runoff and coastal damage affected access routes and terminal connectivity, delaying export cargo movements for days during peak weather impacts. In Indonesia, the same climate phase produced extreme drought. The 2015 fire season burned more than 2.6 million hectares, creating widespread haze across Southeast Asia and reducing visibility along major maritime routes. And so also alters wave and wind patterns across trans-Pacific corridors, forcing vessels to reduce speed or adjust routing during active phases. The Indian Oceans shows variability through a different mechanism. Here, the key driver is the Indian Ocean dipole, a cycle that shifts sea surface temperatures between the western and eastern parts of the basin. During a strong positive phase, warmer waters concentrate near East Africa, while cooler conditions develop near Indonesia and Australia. In 2019, one of the strongest positive events on record brought extreme rainfall to East Africa. Flooding affected transport networks across Kenya and Tanzania, with major disruptions reported around the port of Mombasa, a critical gateway for regional trade. At the same time, the eastern side of the basin experienced severe drought. Australia recorded one of its driest years, with agricultural output and inland transport systems under pressure as water levels dropped across key regions. Cyclone activity in the Indian Ocean is also sensitive to these shifts. Stronger storms in the Arabian Sea in recent years have periodically affected shipping routes and port operations along the coast of India and Oman. Across this basin, temperature gradients translate directly into rainfall extremes, storm intensity, and disruptions to coastal infrastructure. The South Atlantic has always been a demanding region for navigation, but in recent decades, the intensity of conditions has shifted. Stronger winds and more energetic storm systems are now observed across southern latitudes, particularly along routes rounding the Cape of Good Hope. Along the South African coast, ports such as Cape Town and Durban periodically suspend operations during severe weather when high winds and heavy swell make berthing unsafe. These interruptions are not new, but they are occurring within a system where ocean temperatures and atmospheric patterns are no longer stable. As conditions become more volatile, transit planning around southern routes increasingly depends on shorter weather windows and more cautious navigation decisions. This is a way to look at the oceans not as isolated systems, but as the receiving side of a global industrial map. Across northern Europe, the corridor from the United Kingdom through the North Sea to Germany, Netherlands, and Scandinavia forms one of the most concentrated industrial zones on the planet. Heavy industry, energy production, ports, and logistics operate at scale that makes this region a major source of atmospheric emissions moving toward the North Atlantic and the Baltic. On the other side of the ocean, the eastern United States and Canada extend this belt. From the Great Lakes manufacturing region to the Atlantic seaboard, industrial activity feeds into river systems and atmospheric circulation that ultimately connect with the same ocean basin. The largest industrial concentration globally lies in East Asia. The coastal arc from Japan and South Korea down along the Chinese mainland to the South China Sea represents the biggest manufacturing cluster in the world. Energy use, production output, and port throughput all converge along this coastline, creating a continuous zone of emissions interacting with the Pacific atmosphere and waters. A rapidly expanding belt runs along the Indian subcontinent, where major urban and industrial centers line both the Arabian Sea and the Bay of Bengal, linking economic growth directly with the Indian Ocean environment. These regions share a structural reality. Industrial systems operate continuously and at large scale. Unlike transport networks, which can sometimes slow or reroute, energy intensive production rarely adjusts output in response to environmental conditions. The result is a steady release of carbon dioxide, methane, nitrous oxide, and industrial aerosols into the atmosphere. Once emitted, these substances don't remain over their source regions. Atmospheric circulation transport them across basins, where they interact with ocean surfaces through heat exchange, chemical absorption, and deposition processes. This creates what can be described as an influence map, a geography where economic activity in one region translates into environmental effects in another. In this sense, industrial output leaves not only an economic footprint, but environmental one, with oceans acting as one of the primary receivers of that redistributed impact. Let's view an example. If we focus on the North Atlantic, we can see how this invisible map works in practice. The regions surrounding this ocean, North America on one side and Northern Europe on the other, have been among the largest sources of carbon emissions since the industrial era. Together, they account for a very large share of the total carbon released over the time. Air currents carry these gases across the ocean basin. They don't stay over cities or factories, they move with prevailing winds and spread over the Atlantic atmosphere. At the same time, the North Atlantic absorbs more carbon than most other parts of the global ocean. Cold surface waters and strong circulation allow the ocean to take in a significant portion of these emissions each year. What this shows is a direct connection between where energy is used and where environmental change becomes measurable. On a map, this would appear as a band of influence stretching from industrial coastlines into the open ocean. Along the Atlantic and European coast, a pattern is gradually taking shape. In 2023, storms like Siren brought record winds and coastal damage from the Bay of Biscay to the English Channel. Through 2024 and into 2025, repeated winter systems disrupted ports, halted ferries, and forced infrastructure shutdowns across Western Europe. And by 2026, extended periods of rough seas again slowed maritime traffic and exposed how sensitive coastal operations have become to weather volatility. Each event is logged as an extreme episode, but together they begin to show a structural shift. A more energetic ocean does not only reshape shorelines, it reshapes balance sheets. Ports invest more in protection and downtime planning, insurance premiums rise as risk models adjust to higher uncertainty. Maintenance costs increase as infrastructure faces more frequent stress. Even the economics of location begin to change. Coastal real estate, once defined primarily by access and value, increasingly reflects exposure to flooding, to storm surge, and to operational interruption. The shoreline remains a place of connection, but it is also becoming a place where the cost of stability is rising year by year. Not through a single dramatic turning point, but through a sequence of events that slowly reprice risk. If we step back from the events, the data, and the patterns, a clearer conclusion begins to emerge. The challenge we face today is not a lack of information. In fact, we have more observations than ever before. Satellite systems, monitoring networks, real time dashboards, tracking temperatures, currents, storms, and emissions. But these insights often exist in isolation. We analyze one dataset to solve one problem. Then we move to another, building responses piece by piece. The result is a landscape of fragmented decisions, many solutions, yet no single operational picture of how the ocean system and human activity interact as a whole system. What is missing is not another model, but a shared framework, a way to see influence, exposure, and interaction across the entire environment in one coherent view. Not simply maps of weather or charts of emissions, but an integrated representation of how the ocean actually functions as an operating space for society. Such a framework would connect zones of climatic volatility, industrial activity, shipping corridors, and evolving environmental conditions into a single reference for forecasting and planning. Because without that systemic perspective, planning remains reactive. We adjust routes after disruption, we reinforce infrastructure after damage, we reassess risk after losses occur, but the logic of a dynamic ocean demands a different approach, one built on anticipation rather than response. In logistics, this means planning seasonal corridors and reliability windows, using expected volatility to design buffers and resilience into supply chains from the outset. For infrastructure, it means building with trajectory in mind, not only where conditions are today, but where patterns indicate greater exposure in the decades ahead. Economically, it reveals how operational activity translates into environmental impact, allowing decisions to consider both efficiency and system level consequences. In insurance, it shifts risk assessment from retrospective pricing to forward looking evaluation. For investment, it provides a clearer basis for long term decisions about where capital can remain viable in changing environment. And at the policy level, it offers the possibility of coordinating action around shared visibility rather than fragmented response. Seen this way, the goal is not simply climate mitigation, it is the development of a more mature operational understanding of the environment within which global system function. Because when the operating space is understood, risk can be reduced more effectively, decisions become more coherent, and the environmental outcome becomes a consequence of better system design, not only of intention. In that sense, the transition we are witnessing is not just physical, it is cognitive, a shift from observing change to learning how to operate with it. The ocean has never been a static backdrop, but today its role is changing from something we navigate to something we must understand. Not only as a space of movement, but as a system that shapes how economies function, how infrastructure endures, and how societies plan their future. The new ocean is not a distant scenario, it is the environment we are already operating in. And the more clearly we learn to see it, the more capable we become of building with it and not against it.